Triangulene. Triangulene, also known as Clar's hydrocarbon, is the smallest triplet-ground-state polybenzenoid. It exists as a biradical with the chemical formula C22H12. It was first hypothesized by Czech chemist Erich Clar in 1953. Its first confirmed synthesis was published in a February 2017 issue of Nature Nanotechnology in a project led by researchers David Fox and Anish Mistry at the University of Warwick in collaboration with IBM. Other attempts by Japanese researchers have been successful only in making substituted triangulene derivatives. A six-step synthesis yielded two isomers of dihydrotriangulene, which were then deposited on xenon or copper base. The researchers used a combined scanning, tunneling, and atomic force microscope STM/AFEM to remove individual hydrogen atoms. The synthesized molecule of triangulene remained stable at high vacuum, low temperature conditions for 4 days, giving the scientists plenty of time to characterize it, also using STM/AFEM. And triangulenes. Triangulenes, as defined in the previous paragraph, are one case of the wider class of triangulenes, where n equals 123, etc., is the number of hexagons along an edge of the molecule. Thus, derivatical triangulenes may be referred to as three-triangulines. Theory. Huckel or tight-binding description of the molecular orbitals of triangulines predicts that triangulines have n-1 unpaired electrons associated to n-1 non-bonding zero-mode states. When electron-electron interactions are included, theory predicts that the spin-s of the ground state of triangulines is 2s equals n-1. Thus, three triangulines are predicted to have an s equals 1 ground state. The intramolecular exchange interaction that determines the energy difference between the s equals 1 ground state and the s equals 0 excited states is predicted to be maximal among all polycyclic aromatic hydrocarbons pH deradicals on account of the maximal overlap of the wave function of the unpaired spin electrons. The spin of the ground state of triangulines can be rationalized in terms of a theorem. Experiments. Thus far, the ultra-high vacuum on-surface syntheses of triangulines with n equals 3, 4, 5, and most recently 7, the hitherto largest triangulene homologue, have been reported. In addition, the on-surface synthesis of three-triangulene dimers has also been reported, where inelastic electron tunneling spectroscopy provides a direct evidence of a strong antiferromagnetic coupling between the triangulines. References